Hi students, today we will study in detail about Cymbal harmonic motion or SHM. The previous class we studied about Cymbal harmonic motion and what is the criteria for a periodic motion to be a Cymbal harmonic motion. All periodic motions, all vibrations or oscillations are not SHM. The condition for an oscillation or vibration to be a Cymbal harmonic motion is that the force acting, the restoring force acting on the body or the acceleration of the oscillator should be directly proportional to displacement from the mean position. And also it should be always directed towards the mean position. Here this Q is the mean position. When the pendulum is oscillating between the two extreme points P and R, Q is the mean position. At any instant of oscillation, the force, restoring force that you remember mg sin theta, that will be always acting towards the mean position. And the magnitude of force is always directly proportional to displacement from the mean position. So, if the restoring force acting on an oscillator or vibrator, if it is directly proportional to the displacement from the mean position and always it is directed towards the mean position, only such oscillations or vibrations are called Cymbal harmonic motion. And in this class, I am going to explain here in detail about the displacement of SHM and the derivation of equation for velocity of SHM, acceleration, kinetic energy and potential energy. First of all, we have seen from the previous class itself, the displacement of an SHM can be written as y is equal to a sine omega t. And also you know in detail about this equation. This y represents the displacement of the oscillator at any instant of time. It can be at the mean position or in between the mean position and extreme position. So at any instant of time t, the y will be keep on changing. Here a is the maximum amplitude, maximum displacement towards one side, that is called amplitude of the oscillator. Here this much is the amplitude, that is the maximum displacement on either side of the mean position. And omega is the angular frequency and t is the time variable. So this equation gives us the position or displacement of the bob at any instant of time. For a given oscillator, omega will be constant, amplitude will be constant, only time is the variable. So if you apply the value of the constants, the amplitude and angular frequency, then at any instant of time we can locate the position of the bob here, whether it is at the mean position or the extreme position here or the opposite side extreme position, that can be obtained by applying the value of time. So at any instant of time we can obtain the y, that is the position of the bob on either side, from the equation y equal to a sine omega t. So this equation represents the displacement equation of the Cymbal harmonic oscillator. Now the second equation, we have to derive an equation for velocity. We know that the equation for instantaneous velocity, v is equal to dy by dt, where dy is a infinitesimally small, a very small displacement in y direction in a small interval of time dt. So the displacement by time, that will give the acceleration of the body. So in this equation, v is equal to d by dt of, for y we can substitute the value a sine omega t, a sine omega t. In this equation, a is a constant, omega is also a constant. So when we differentiate this equation, it will come a into when we are differentiating sine omega, A is a constant that can be taken outside the differential. So A into, when we differentiate sine omega t, in that omega is a constant again, that also should be taken outside omega. Then differential of sine omega t is cos omega t. So we'll get the equation of velocity of an oscillator as a omega into cos omega t. Now we can slightly modify this equation. We know that cos square theta is equal to 1 minus sine square theta. So cos theta will be equal to square root of 1 minus sine square theta. Here we have, instead of theta we have taken omega t. So we can write cos omega t is equal to under root 1 minus sine square omega t. So if you substitute that value here, we can get the equation of velocity v is equal to a omega into square root of cos omega t can be written as 1 minus sine square omega t. Okay, so the equation becomes a omega into under root 1 minus sine square omega t. Now what I am doing, I am multiplying this a inside the square root. So when we take this a into the square root, it should become a square. Then only outside the square root become a. So the equation v equal to velocity of the oscillator is equal to omega into, I am taking a inside the square root, so it becomes square inside. So 1 into a square become a square minus a again here with the sine omega t, a square sine square omega t. Now in this equation we can see here a square sine square omega t, but y equal to a sine omega t. Okay, a square sine square omega t, y equal to a sine omega t. So a square sine square omega t, a square sine square omega t will be equal to y square. Means we can write the equation of velocity v is equal to omega into square root of a square minus y square. So this is the equation for velocity of an oscillator. The velocity of an oscillator, SHM, simple harmonic oscillator, is v is equal to omega into root of a square minus y square. Now we can see the special cases. Suppose initially the oscillator is at this position, mean position. At that mean position, the value of y is equal to 0. If y equal to 0 in this equation, then v becomes v is equal to omega into square root of a square minus 0. Because at this mean position there is no displacement, y is 0. So when we apply y equal to 0, this equation becomes omega into root of a square is a. This is the maximum value of velocity v max. So when a oscillator, when a simple pendulum oscillates in between two extreme position, its velocity will be maximum at the mean position. While it's oscillating, maximum velocity will be at the mean position, that will be equal to omega into a. Now, at the extreme position, when the bob reaches here, its displacement y is equal to a. Y is equal to a. So when we apply that in this equation, its velocity v is equal to omega into square root of a square minus a square. So a square minus a square equal to 0 means v is equal to 0. It means at the extreme position, the bob will become 0, the velocity of the bob becomes 0, it will stop, again it will return back. So at the mean position, velocity is maximum. At the extreme position, when it is moving towards the extreme position, the velocities keep on decreasing. When it reaches at the extreme position, it stops and again it returns back towards the mean position. And when it reaches at the mean position, its kinetic energy becomes maximum, and because of that high kinetic energy, it will start moving in the opposite direction. When it moves opposite direction, the restoring force is acting in the reverse way, so the velocity will keep on decreasing and finally again it will stop here. So in between the two extreme portion, it will start oscillating. If there is no dissipation of energy, if there is no loss of energy due to the external friction, like friction of air, air drag, etc., if it is not having any external force, it will be keep on oscillating with undamped oscillation. It is called undamped oscillation with a constant amplitude. Now, this much you have to remember about the velocity of an oscillator. Here, once again, the expression for velocity, and that is v is equal to omega into root of a square minus y square, and from that equation we can find out the maximum velocity at the mean position and the minimum velocity 0 at the extreme position, and in between that two position we can have any value of velocity by applying the value of y in this equation. Now we can see the third quantity, that is acceleration of the oscillator. So once again we'll start with the displacement equation. The displacement of the oscillator is y is equal to a sine omega t. And after differentiation, we got the equation of velocity. The velocity equation we got, it was a omega into cos omega t. This equation we modified in the form of omega into root of a square minus y square. Now this is the actual equation of velocity, a omega into cos omega t. Now we know that acceleration is equal to rate of change of velocity, that is dv by dt. When we differentiate velocity with respect to time, we will get acceleration. So the acceleration of the oscillator, a is equal to d by dt of, instead of v, I can substitute the value of velocity, that is a omega into cos omega t. In this equation, a omega is constant. Inside cos function also, this omega is constant, only time is the variable. So when we differentiate this equation, acceleration a is equal to this a omega. First of all we have to write, they are constants. Then when we are differentiating cos omega t, again one omega is there, that also should be taken outside, and cos omega t differential is minus sine omega t. So the equation of acceleration becomes a is equal to minus a omega into omega, omega square into sine omega t. Here we can see minus a omega square into sine omega t. But we can see here a sine omega t is y. Here also we have a sine omega t. So this equation can be written as acceleration is equal to minus omega square into a sine omega t. This a sine omega t is nothing but the displacement of the oscillator. So the final equation of acceleration can be written as a is equal to minus omega square into y. This is the equation of acceleration of a simple harmonic oscillator. That is a is equal to minus omega square into y. In this equation, when we apply the conditions, we can get the value of minimum acceleration and maximum acceleration. Suppose first case, we are applying this condition, this equation at the mean position. When the particle reaches at the mean position, the acceleration a equal to minus omega square y. Acceleration a is equal to minus omega square into y. At the mean position, displacement is equal to 0. Y equal to 0, no displacement at the mean position. When we apply in this equation y equal to 0, we will get acceleration equal to 0. Means at the mean position, acceleration is equal to 0. The reason is that we know that the restoring force acting on the pendulum, on the bob, at this point is 0. When it is displaced this way, then only restoring force will start in the opposite direction. So at the mean position, it is an undisturbed position. There is no restoring force acting, and if there is no force acting, there is no acceleration. According to Newton's second law, for acceleration there should be a force F equal to ma. Here there is no force acting, no restoring force, so acceleration will be 0. Means at the mean position, during the oscillation, at the mean position, always acceleration will be 0. And also we have seen from the equation of velocity v equal to omega into root of a square minus y square, At the mean position y equal to 0, then v equal to omega into a. Root of a square is a, so v equal to omega into a. Means at the mean position, velocity is maximum. Velocity is maximum, but acceleration is 0. So this is a special case at the equilibrium point. Velocity is maximum, but acceleration is 0. The reason is that at the equilibrium point, there is no force acting on the oscillator, so acceleration cannot be there. For any way, for getting acceleration, there should be a force. No force is there on the bob at the equilibrium point, at the mean position, so acceleration is 0. But velocity is maximum at the mean position or equilibrium point. And if we apply the second case at the extreme position, suppose the bob reached here, that at extreme position, the displacement y is equal to amplitude a. Then we can see here acceleration a is equal to minus omega square into y is equal to a. This is the maximum acceleration, a max. Maximum acceleration is equal to minus omega square into a. And we can see here at the extreme position, when we apply velocity equation, v equal to omega into root of a square minus at this extreme point y equal to a square minus a square 0, velocity is 0. Means at the extreme point, the velocity of the oscillator is 0, but acceleration is maximum. And also we can see in this equation, this acceleration is, omega is a constant. For a oscillator, omega is constant. So acceleration is directly proportional to y, displacement. Means when this displacement increases, acceleration is increasing. At the extreme position, it becomes maximum, that is minus omega square into a. When it returns back, acceleration decreases. And at this point, acceleration becomes 0. So at the extreme point, velocity is 0, acceleration is maximum. At the extreme point, velocity is 0, acceleration is maximum. At the mean position, acceleration is 0, velocity is maximum. So this is one special case at the extreme point. If you are getting a question that give an example for a body which is having 0 velocity but non-zero acceleration. One example is this one. When a body is oscillating, when a pendulum is oscillating, at the extreme point, for the bob of the pendulum, velocity is 0 but acceleration is maximum. Just like when we are throwing a body upward, at the maximum height, velocity becomes 0 but acceleration is the 9.8 downward direction. Now we can see the fourth quantity, that is the kinetic energy of a oscillator, Cymbal harmonic oscillator. We have the equation. We know that kinetic energy of a body is given by Ke is equal to half mv square, where m is the mass of the bob in the case of a pendulum and v is its velocity. So kinetic energy is equal to half mv square. And for a Cymbal harmonic oscillator, the velocity at any instant of time is given by v is equal to omega into root of a square minus y square. A square minus y square. At any instant of time, if you apply the value of y, displacement, 0 or maximum or any other value, we will get the velocity at that particular instant of time. So here we have to derive an equation for kinetic energy of the oscillator. So for kinetic energy of the oscillator, Ke is equal to half into mass of the oscillator m into square of the velocity. Velocity is omega into square root of a square minus y square. So we can write omega into square root of a square minus y square. Square of that whole square, because it is v square. So v is omega into root of a square minus y square. So v square will be the omega into root of a square minus y square whole square. When we square this equation, the equation becomes kinetic energy is equal to half m into omega square into root of a square minus y square whole square will be a square minus y square. That is, square of omega is omega square and square of root a square minus y square is become a square minus y square. So the equation for kinetic energy is half m omega square into a square minus y square. This equation gives the kinetic energy of the oscillator at any instant of time during the oscillation. And here also, when we apply the condition, suppose the first case, suppose we are taking the mean position at this point Q, at the equilibrium point. At the mean position, y equal to 0. When we apply here y equal to 0, we will get the kinetic energy equation Ke is equal to half m into omega square into a square minus 0. Or we can write this kinetic energy, this is the maximum kinetic energy, Ke max, kinetic energy maximum, that is equal to half m into omega square into a square. This gives the maximum value of kinetic energy. That is kinetic energy maximum, the maximum value of kinetic energy Ke max is equal to half m into omega square into a square. This is the maximum value of kinetic energy. Okay? Maximum value of kinetic energy Ke max is equal to half m omega square a square. Now, if we apply the same condition at the extreme point, if we are applying the same condition at the extreme point, that is at the extreme point, that is the second case, at the extreme point, K is equal to half m omega square into a square minus, at the extreme position at the extreme point, y equal to a, the displacement y become a, that is a square minus a square. So a square minus a square equal to 0 means kinetic energy is equal to 0. Means when a bob is oscillating, when a pendulum is oscillating, its kinetic energy is maximum at the equilibrium point, mean position, that is equal to half m omega square a square. And at the extreme point, kinetic energy becomes 0 because at the extreme point, y equal to a, displacement equal to amplitude. When displacement y become amplitude, maximum displacement, a square minus a square equal to 0, so kinetic energy is 0. Means when the bob is oscillating, when it at the equilibrium point, kinetic energy is maximum. When it is moving towards the extreme point, kinetic energy gradually decrease and become 0. So eventually potential energy will be increasing and becoming maximum at the extreme point, that we can see in the next expression. Now we have to derive an equation for the fifth quantity, that is potential energy. So for that purpose, suppose first of all I am displacing the bob through a small distance, a small displacement y from the mean position. When it is displaced through a distance y, a restoring force will act in the opposite direction, and that restoring force F is proportional to y, or that F is equal to minus ky. Here the negative sign shows that the restoring force is acting towards the equilibrium position, means opposite to the displacement, and it is directly proportional to y, means the displacement increases, restoring force also will increase. So right now at this position, minus ky is the restoring force acting, where k is called the force constant of the oscillator. Now imagine from this point I am displacing the bob further a small distance, a very infinitesimally small distance, say dy. For that purpose, since minus ky is the force acting towards the mean position, to displace in the opposite direction, I should apply a plus ky force in the opposite direction. So I am doing a small amount of work to displace the bob from this point to this point through a small displacement dy by applying a force plus ky in that direction. So the small amount of work done, dw, is equal to the applied force plus ky into displacement dy. Force into displacement. Work done is equal to force into displacement. So ky is the small amount of force applied and dy is the displacement. Ky into dy, that is a small amount of work done in displacing the box through a small, infinitesimally small displacement dy. Now imagine that we are displacing from the mean position to a larger displacement, then the total work done W can be obtained by integrating this expression, that is W integral of dW. Means the total work done W is equal to integral of dW is ky dy. Ky dy. When we integrate this equation, the total work done W is equal to k is a constant and integral of y dy. Integral of y dy is y square by 2. So the total work done W is equal to k into y square by 2. K into y square by 2. Here we can apply the limit for y. It can be from 0 to maximum according to the situation. So right now we are taking the equation of work done as ky square by 2, or we can say it is half ky square. This work done will be stored in the box as its potential energy. So potential energy of the oscillator P is equal to the work done in displacing against the restoring force, that is half ky square. So half ky square is the equation for force acting. Half ky square is the equation for the potential energy of the Cymbal harmonic oscillator. At any instant of time, the value can change. We can modify this equation by a small way. We know that equation for force according to Newton's equation, F is equal to ma, mass into acceleration. And in the case of an oscillator, the force acting F can be written as F is equal to mass into acceleration equation already we derived, that is minus omega square into y. So m into, instead of acceleration and substituting this value, minus omega square into y. And also we have this equation, the restoring force acting, the acceleration is given by the restoring force, that acceleration is given by the restoring force, F is equal to this equation minus ky. So we have two equations for the force acting on the Cymbal harmonic oscillator. One is from Newton's second law, that is minus m omega square y. Another from the Hooke's law, that is F is equal to minus ky. On equating these two equations, that is minus ky is equal to minus m omega square into y. This y will get cancelled. We will get the value minus also cancelled. We will get the value of k is equal to m omega square. We can substitute that value here in the equation of potential energy. K is equal to m omega square. So the potential energy equation P is equal to half into k is given the value m omega square. So m omega square into y. So equation for potential energy is half m omega square into y, half ky square. This k can be replaced by half k is m omega square into y square. Half m omega square into y square. Half m omega square into y square is the equation for potential energy of a Cymbal harmonic oscillator. Now we apply these special cases. When we apply the special cases, suppose we are taking the points like the mean position, the equilibrium point. At the equilibrium point, the displacement y is equal to 0. So in this equation, if I put y equal to 0, then potential energy Pe is equal to 0. Potential energy become 0. Means at the mean position, potential energy of the oscillator is 0, and what we have seen from the previous equation of kinetic energy, at the mean position y equal to 0 and kinetic energy is half m omega square a square, that is maximum value. So at the mean position, potential energy is 0 and kinetic energy is maximum. If you take the second case, that is at the extreme point. At the extreme point, y equal to a. So from this equation, potential energy half m omega square into y square. Y we can substitute a. So the equation becomes potential energy at the extreme point P is equal to half m omega square into y square. Instead of y, we are putting maximum value of y is at the extreme point is a square. So half m omega square a square. This is the maximum potential energy at the extreme point. So at the mean position, potential energy is 0. At the extreme position, potential energy is maximum, PE maximum, that is coming at the extreme point. Now we can compare these two equations. We have got before, kinetic energy is maximum at the equilibrium point. That maximum kinetic energy we got half m omega square a square. Now here we are getting at the extreme point. At the extreme point, maximum potential energy is also equal to half m omega square a square. See the two equations. At the mean position, kinetic energy maximum is half m omega square a square. At the extreme position, maximum potential energy is half m omega square a square. So we can see here, energy is neither created nor destroyed. At the mean position, it is completely kinetic energy, that is half m omega square a square. At the extreme position, it is completely potential energy, that also half m omega square a square. In between extreme position and mean position, there will be both kinetic plus potential, and that total energy we can obtain by adding the equation of potential energy and kinetic energy. So what we are seeing here, at the mean position, kinetic energy is maximum, that we got kinetic energy maximum is half m omega square a square. And at the extreme position, potential energy is maximum, that potential energy maximum is also equal to half m omega square a square. Now in between these two, extreme position and mean position, we can take any one point here. At that time, there will be both kinetic energy and potential energy. So the total energy of the oscillator at any point in between extreme point and mean position, the total energy is equal to sum of the kinetic energy plus potential energy. That is, total energy is equal to, we have the equation for kinetic energy, that is half m omega square into a square minus y square. Total energy is equal to kinetic energy is half m omega square. At any position, the kinetic energy is half m omega square into a square minus y square plus, at any position, at any point in between extreme position and mean position, the potential energy is half m omega square y square. That is plus half m omega square y square. So we can see here, when we expand this equation, that is total energy is equal to half m omega square into a square, opening the bracket, minus half m omega square into y square, half m omega square into y square, plus potential energy, half m omega square y square, half m omega square into y square. This minus half m omega square y square and plus half m omega square y square get cancelled. What is remaining here? Total energy is equal to half m omega square into a square. See here. At the extreme point, the maximum potential energy is half m omega square a square. At the mean position, maximum kinetic energy is half m omega square a square. In between extreme point and mean position, anywhere in between, there is both potential energy as well as kinetic energy. When we add both of them, kinetic energy plus potential energy, the total energy also becomes half m omega square a square, half m omega square a square. It means energy is neither being created nor be destroyed. It is only changing from one form of energy into another form. At the equilibrium point, mean position, it is only kinetic energy. When it moves towards the extreme point, kinetic energy decreases, but potential energy increases. At the extreme point, potential energy becomes maximum, kinetic energy becomes zero. So in between that, there is both potential and kinetic, but we can see the total energy at the mean position is half m omega square a square. Total energy at the extreme position is also half m omega square a square. In between these 2 points also, total energy is same. Means energy remains constant throughout. But we can see extreme position, potential energy is maximum and kinetic energy is zero. At the mean position, potential energy is zero and kinetic energy is maximum. Now we can see the variation of kinetic energy and potential energy on a graph. In this graph, I am taking the displacement of the oscillator, this displacement on the y-axis. Now we can see the variation of this kinetic energy and potential energy on a graph. In this graph, on the x-axis, I am taking the displacement of the bob in this direction. So the displacement y is taken along x-axis. And the energy of the oscillator I am taking on y-axis. Energy is taken on y-axis and displacement along x-axis. This energy taken on y-axis, it can be kinetic energy, potential energy or the total energy. Now when we consider the kinetic energy, equation of kinetic energy, at the mean position we have seen mean position y equal to 0, then kinetic energy become maximum. So kinetic energy, this black curve represents the variation of kinetic energy. At the extreme position, when at the extreme position y equal to a, when y equal to a square minus a square 0, means at the extreme position kinetic energy is 0. Means at this two extreme point, kinetic energy is 0. So this black curve represents the variation of kinetic energy. At the extreme position, kinetic energy is 0. When the bob move towards the equilibrium point, this is the equilibrium point, the mean position, the kinetic energy keep on increasing, and at the equilibrium point, means at this point, kinetic energy become maximum, this much maximum. And that value is half m omega square a square. So this black curve represents the variation of kinetic energy. At the extreme point it is 0, at the mean position it is maximum. And this red curve represents the variation of potential energy. In potential energy equation from half m omega square y square, at the mean position y equal to 0, so half m omega square y square 0. So at the mean position potential energy is 0, but the extreme position potential energy become maximum. When the bob reaches here, it stops, so kinetic energy becomes 0, but potential energy is maximum, height is maximum, potential energy is maximum. So this curve represents at the extreme point maximum potential energy, at the mean position 0 potential energy. And also we can see this horizontal line, that black line, it represents the total energy. If you add potential energy and kinetic energy at any instant of time, that will give the total energy. At this mean position, there is only kinetic energy. So the kinetic energy curve is touching the total energy. At the extreme point, there is only potential energy, no kinetic energy. So the potential energy curve is touching the total energy. So at other points, we have kinetic plus potential. When we add these two, that will be equal to the total energy. Means the total energy remains constant throughout. It is a horizontal line parallel to x-axis. So there is no change in total energy. But kinetic energy and potential energy will keep on change, and total energy will remain constant. So this is the total explanation of Cymbal harmonic oscillation